Hello, scholars. Today we're going to look at 1-7 inverse relations and functions. And our learning targets for today are, I'm learning to use the horizontal line test to determine inverse functions, and I'm learning to find inverse functions algebraically and graphically. So let's take a look at inverse functions. First, we have an example of a relation shown in both Table A and Table B. Take a look. Do you notice anything between Table A over here and Table B over here? Well, if you said that your tables are actually just flip-flops of each other, or inverses, you'd be absolutely correct. For instance, when you take a look at this x variable of tickets, you see that we have 1, 2, 3, 4, and 6. And if you take a look at the y variable over here of tickets, we have the same values, 1, 2, 3, 4, and 6. And the same goes for money spent and cost. So they are actually considered inverse relations because we switched our domain and ranges. So inverse relations exist if and only if one relation contains BA whenever the other relation contains AB. When a relation is expressed as an equation, its inverse relation can be found by interchanging the independent and dependent variables. So let's take a look at an example. It says, find and graph the inverse relation of y equals x squared minus 4. We're going to do this both graphically and algebraically. So let's start off graphically. And to do so, we're going to make a nice t-chart. Here we have x and y. So let's go ahead and make sure we choose values that are on both sides of our 0, negative and positive. So I'm going to go -3, -2, -1, 0, 1, 2, 3. All right, so now I'm going to just show a little bit of work here. We have y equals x squared minus 4. Now let's substitute in that -3. So -3 squared minus 4, we get 9 minus 4, which is 5. So now we have a y value of 5. And now we're going to continue this on. But instead of -3, we're going to put -2. So now I have -2 squared, which is 4 minus 4, which is 0. So now -2 is 0. I'm going to do the same thing with -1. -1 squared is 1 minus 4. We get -3. So -1 is -3. All right, now let's try it for 0. 0 squared minus 4 is 0 minus 4, which is -4. And from here, you should be able to do the rest of the values. And I'll go ahead and I'll fill them in. I have -3, 0, and 5. So the first thing I want you to do is go ahead and plot these ordered pairs. -3, 5, so -3, +5, -2, 0, -1, -3, 0, -4, 1, -3, 2, +0, and 3, +5. And go ahead and draw me that continuous function, please. All right, it's not the prettiest, but it is a parabola. And I'm going to label this f of x, or in this case, y. So that is my original function. Now, to graph the inverse, f -1 of x, we're going to take that same xy chart that we made, but we're going to flip-flop our x and y values. So now it's 5, -3, 0, -2, -3, -1, -4, 0, -3, 1, 0, 2, and 5, 3. All we did was interchange those dependent and independent variables. So let's go ahead and graph f inverse. So we have 5, -3, 0, negative 2, negative 3, negative 1, negative 4, 0, negative 3, 1, 0, 2, and 5, 3. And go ahead and graph this. All right, so I graphed the inverse, and we're going to label this one f inverse of x. So that is the graphical way to find the inverse. Now, what do we have to do for algebraically? The concept is still going to be the same. Originally, I had y equals x squared minus 4. However, to solve the inverse algebraically, you're going to switch your x's and your y's. So now I have x equals y squared minus 4. And my goal is still going to be to get y by itself. So to do that, I'm going to add 4 to both sides. So now I have x plus 4 equals y squared. And how do I get a y by itself if it's being squared? You take the square root. And when you take the square root, you end up getting a plus and a minus radical x plus 4. And that's going to give you your f inverse. So here is your f of x, and here is your f inverse of x. All right, but Miss Younger, how am I supposed to know if it's going to have an inverse function? Now, graphs will have inverses, but whether or not those inverses are functions are a totally different story. Now remember, when it comes to functions, they have to pass a vertical line test. Now, to determine if your function has an inverse function, it'll have to pass the horizontal line test. And basically it says if your graph touches more than once through a horizontal line, then it will not have a function that isn't, or it won't have an inverse that is a function. It'll have an inverse, it will not be a function though. So we're going to go ahead and graph these two functions. So let's take a look. We have the absolute value of x minus 1. So using my knowledge of transformations, this one's pretty easy. I probably don't need a graphing calculator for this one. I know that it's an absolute value function, so it's going to be a V-shaped, and I know I'm going to the right one, and that's going to be my vertex. All right, so now I'm going to graph. Oops, I went to the left one. My bad. And I'm going to graph the absolute value function. All right, so here's my absolute value function. Let's see if it passes the vertical line test, or the horizontal line test, to determine if my inverse is a function. So let's draw a horizontal line. So here I have this horizontal line going across. Does it touch in more than one spot? Yes, it does. And because it touches in more than one spot, here's the issue. So, yes, an inverse exists, but it is not a function. So that means if I were to graph that inverse, it would fail the vertical line test. Because it failed the horizontal line test, its inverse would fail the vertical line test. All right, so now I have g of x equals x cubed minus 6x squared plus 12x minus 8. It says using a graphing calculator. I can't do this transformation in my head. So let's go ahead and use that graphing calculator. So I'm going to go to my Desmos calculator because that's my free online calculator that I love, love, love to use. And I'm going to type in x caret 3 minus 6x caret 2 plus 12x minus 8. All right, so there's my function. There's the graph. It looks like it switches directions at the point 2, 0. So let's go ahead and sketch that on our coordinate plane that we have in our notes. All right, so we know that we're going to have a change of direction here at 2. So let's just go like this and maybe like that. We changed our direction. Is it perfect? No, it is not perfect. It doesn't, it represents the general idea of that function, but here's the key word. We're supposed to sketch. It's not going to be perfect because we're doing it by hand. Now, will this one pass that horizontal line test? Let's take a look. Anywhere on my graph, if I draw a horizontal line, does it only touch once? And the answer is yes. No matter where I put that horizontal line, it will only touch once. So we're going to say yes. The inverse is a function. So horizontal line test is really, really awesome. All right, so if a function passes the horizontal line test, then it is said to be one-to-one. You should remember that from Algebra 2. So if it passes the horizontal line test, it is said to be one-to-one because no x value is matched with more than one y value and no y value is matched with more than one x value. If a function f is one-to-one, then the inverse function such that the domain of f is equal to the range of f of -1. Basically, we're just saying this all over again in fancy terms. Now we're going to practice finding that inverse algebraically once again. Remember from our example beforehand, we're just going to interchange those domains and those ranges. So here's our first example. Here we have f of x equals x minus 1 over x plus 2. Here we switch our domains and our ranges, or that, not domain and range, my apologies, my independent and dependent variables. So instead of y equals x minus 1 over x plus 2, I have x equals y minus 1 over y plus 2. My goal is to get y by itself. So first things first, let's get rid of this denominator of y plus 2. So to do that, I'm going to have to multiply both sides by the quantity y plus 2. All right, so when I multiply on the left-hand side, that x distributes, and I get xy plus 2x equals y minus 1. And that's because, boom, when I multiply and divide by the same quantity, they're going to cancel each other out. So now I want all my y's on one side and all my x's on the other. So let's go ahead and move this y over here. So I'm going to subtract 2x from this side, but then subtract y from this side. So now I have xy minus y equals -1 minus 2x. Now notice I have an xy minus y. Both terms have y values. So using my greatest common factor, I'm going to factor out a y variable. When I take out a y from xy, I'm left with x. If I take out a y from y, I'm left with just that -1 placeholder. All right, now I'm finally down to the 1y, and I'm going to divide both sides by that x minus 1 so I can get that y back to being by itself. These ones cross out, and now we have y equals -1 minus 2x over x minus 1. All right, so remember, our domain of f of x said that x can't equal -2. But now our domain of the inverse says x can't equal 1. So we go from -infinity to +1 and 1 to +infinity. And that's because, if you recall, we set this bottom value equal to 0, and that says, hey, x can never equal 1, or else we'll end up with that 0 in our denominator, which is an undefined value, which is not allowed. All right, so going on to the next example, we have f of x equals the square root of x minus 4. So we're going to switch our x's and our y's. All right, how do I get rid of a square root? If you said, hey, Miss Younger, you need to square both sides, you would absolutely be correct. We square both sides, we get x squared equals y minus 4. We need to get y by itself, so we add 4 to both sides. And now we have x squared plus 4 is y. This is my inverse of x. All right, are there any restrictions on my domain? Yes and no. Well, take a look. F of x had a restriction. It said, hey, it can't equal 4. But what does that mean for inverse of f? Well, let's take a look at that domain. That domain and range of f of x. Well, the domain said, hey, you can't equal 4. It has to be bigger than 4. So we have 4 to infinity. But our range said this was a square root function, and we know that we can't have any negative y values, which means our smallest is going to be 0. Well, if you think about it, if we're interchanging our independent and dependent variables to find the inverse, you also find and switch the domains and ranges. So now they flip-flop. 0 to infinity is the domain, and the range is 4 to infinity. Easy peasy, right? Going on, we're going to try and figure out if we can determine if two functions are inverses. So here's the deal. For two functions f and g to be inverses, that means that if I were to substitute g of x into f of x and f of x into g of x, they would both yield the same answer of a single solitary x. So what do I mean by this? Well, we're going to go back to function compositions. And we're going to do this twice so you can see that it works both ways. So we're going to do f of g of x first. So we have 6 over, and instead of x, we're going to put 6 over x plus 4 minus 4. All right, now if we simplify, plus 4 minus 4, we know the plus 4's minus 4's cancel. And now I'm left with 6 over 6 over x. Well, when we have a fraction in the denominator, we can multiply by its reciprocal to get it out. So what ends up happening is I get 6 times x over 6, because x over 6 is the reciprocal of 6 over x. The 6's cancel, and I'm left with an awesome value of just x. So far we know that g is the inverse of f, but is f the inverse of g? To find that, we just work in the opposite direction, putting f of x in. So now we have 6 over x minus 4 plus 4. We're going to multiply by that reciprocal just like we did beforehand. So x minus 4 over 6 plus 4. Well, these 6's cancel out. I'm left with x minus 4 plus 4. These two minus 4's plus 4's cancel out, and I'm just left with the value of x. So based on this, we can say that f is the inverse of g, and g is the inverse of f. All right, so now we're going to take a look at finding the inverse graphically. And to do that, we actually draw the line y equals x, which is straight through the origin. So now all you're going to do is you're going to reflect across the line y equals x to find f inverse. So if I'm at 0, 1, I'm going to be at 1, 0. If I'm at negative 1, 0, I'm going to be at 0, negative 1. If I'm at 1, 2, I'm going to be at 2, 1. And so basically, we're just doing the opposites. And we know they're going to cross here at this point. So go ahead and draw it. All right, so drawing it out, here is our inverse of x. We just took and flip-flopped those x's and y values. Or, in other words, we reflected across the line y equals x. All right, for our last example, it says, Kendra earned $8 an hour, works at least 40 hours per week, and receives overtime pay at 1.5 times her regular hourly rate for any time over 40 hours. Her total earnings f of x for a week in which she worked x hours is given by the function f of x equals 320 plus 12 times quantity x minus 4. So, explain why the inverse function exists. Notice, it's not asking if an inverse it's not asking if an inverse exists. It's asking if an inverse function exists. So we have to see if it passes the horizontal line test. So if I take a look, if I draw a horizontal line anywhere, it will pass. So it passes the horizontal line test. And then it actually wants us to find that inverse. So just like before, we're going to flip-flop our x's and our y's. So x now equals 320 plus 12 times y minus 40. First things first, let's subtract 320 from both sides. So now I have x minus 320 equals 12 times y minus 40. Well, if I'm trying to get this y by itself, let's go ahead and distribute that 12. So now I have x minus 320 equals 12y minus 480. All right, next thing we're going to do is add 480 to both sides. So now I have x plus 160 equals 12y. Now we're going to divide every single term by 12 so we can finally get that y by itself. So when that happens, we end up getting a function of f inverse of x equals x over 12 plus 160 over 12. Well, what does it mean? What do f inverse of x and x represent in the inverse function? So originally we had our time being our x and our earnings being our y. But when we flip-flop those to find f inverse, our x is now our earnings. So x represents Kendra's earnings for the week, which means f inverse represents the hours worked. All right, now it says what restrictions, if any, should be placed on the domain of f of x and f inverse of x. So if we take a look at f of x as it is, do we have any domain restrictions? Well, we actually do. We know that she works at least 40 hours a week, which means we can actually include the number 40. Whoops. So we have 40. Now, is there a maximum number of hours that she can actually work? If you said yes, then you would absolutely be right. 168 is the absolute highest number of hours she can work because that is how many hours are in a week. So let's take a look at our F inverse domain. But to do that, we have to find the range of f of x first. So if I were to work 40 hours, the minimum Kendra could earn would be a total of $320. But if she were to work every single day of the week, she would now earn, or every single hour of the week, she'd now earn $1,856. So remember, when we find the inverse of f, it flips our domain and range. So now our domain is 320 to 1856. And then last but not least, the final part of our example says find the number of hours Kendra worked last week if her earnings were $380. So you actually take the f inverse function of 380. So we know that is 380 divided by 12 plus 160 divided by 12. Which, when we stick it into our handy dandy calculator, gets us a nice solid number of 45, which means Kendra worked 45 hours. All right, so that's it for our notes today. If you have any questions, please do not hesitate to ask. I am here to help. You can send me an email or you can pop into Teams and ask me questions. All right, you have a great day.